7.1C, regular payments of an annuity. Okay, so we're just going to recall the two equations that we went over in 7.1A and B. So we took a look at future value, okay, what something's going to grow to in the future. So this is to find the value at the end of an annuity, okay, after all the deposits are made and the interest has occurred. And then we took a look at present value. Okay, and this is to find money needed at the beginning of an annuity to provide regular annuity payments. Okay, so it's present value and it's based on the amount of money you put in at the regular intervals. Okay, calculating regular payments of an annuity. So we use the future value of an annuity formula and isolate for R. Okay, so if we want to determine payments, okay, so what we're talking about is determining the R given the future value. Okay, what we'd have to do is we'd have to cross multiply. So A here is in the numerator, and we would have to take this bracket here and cross it down. Okay, so we get A over square bracket 1 plus I, the exponent n minus 1, square bracket, and we would have to cross multiply this I up. And that would equal R. So this is how we would determine the payments, which is obviously R, right? R is the payments. Now determining payments given the present value. So it depends on what we're given. If we're given the amount, we use this formula. If we're given the present value, we use this formula. And again, this PV is in the numerator. We're going to cross multiply this bracket down. So it's going to be PV all over square bracket 1 minus bracket 1 plus I to the negative n. And we're going to cross multiply this I up to the numerator. Okay, so depending on what you're given, when we want to determine the payments, we use one of these two formulas. Example 1, determining payments given the future value. So in this question, we're going to be given the future value. I'm just going to kind of skip ahead over here, and I'm going to write out the formula that we use. Okay, so this one's going to be R equals AI. Okay, so future value is just A, the amount that it's going to grow to be. Oh, 1 plus I bracket to the n minus 1. Okay, so Brienne wants to save $6,000 for a trip. Okay, so that's the future value. She needs $6,000 in the future. Okay, or we can call this A. She plans to take in 5 years. Okay, so she wants to take it in 5 years from now. What regular deposit should she make? So we don't know the R, the regular deposit. Should she make at the end of every 6 months? Okay, so this is 2 times a year. 2 times per year. Into account earning 6% per year, compounded semi-annually. So semi-annually is just that 2 times per year. These are always going to be consistent when she's making the deposits and when it's compounded. Okay, so the interest is 0.06, and she gets this twice a year. Okay, but she doesn't get the 6% twice a year. She'll get 3% twice a year. Now, it's every 6 months, so it's 5 years from now, twice a year. She's going to be paid this 3% 10 times. So now let's actually just sub these numbers in. So I get 6,000 times 0.03 all over big box bracket 1 plus 0.03 to the exponent 10 minus 1. Okay, and then I get 180, so I just multiply the numerator and then figure out the denominator, 0.3439. Okay, and that gives us 523.38. Okay, so these are going to be her deposits. Therefore, she needs to make deposits of $523.38. Okay, and that's A. Now let's take a look at B. How much does Brianne save altogether? Okay, so the amount that she's actually putting in, remember she's putting in $523.38, and how many times does she put that in? Well, she invests that 10 times. So she's actually saving $52.33.80. And see, how much interest does she make? Well, if she actually put in $52.33.80 and she needs $6,000, that's what's actually going to come out of it, then what we can do is we can find the difference between these two, which is $766.20. So we can say, therefore, she invests, so she personally invests $52.33.80 and makes $766.20 interest. Okay, last one. Determining payments given the present value. Okay, so this is going to be the other equation. This is going to be determine the payments. Payments is R. We're given the present value, and we're going to use this formula. Okay, Donald borrows $1,200 from an electronics store to buy a computer. So the present value, he owes $1,200. He will repay the loan in equal monthly payments. So monthly is 12 times a year over 3 years. So that means that he's going to be making 36 payments starting 1 month from now. This is fine. All this means is that the ordinary simple annuity is getting paid at the end of the compounding period, so the end of the month. He's charged interest at a rate of 12.6%, so that's very high. And then that's compounded monthly. So when we actually divide those out, every single month, he's going to be paying 0.0105. Okay, so for A, how much is this payment? So we're actually going to solve for R here. So the present value is $1,200. He's paying 0.0105. And then we're going to put this over 1 minus 1 plus 0.0105 raised to the exponent negative 36. Okay, when we multiply the top, we get 12.6. When we multiply the bottom, we get 0 decimal. And I left a bunch of these numbers for the interest just so that it's more accurate. Okay, so he's going to be paying payments of $40.20. Therefore, his payments are 40.20. Okay, so if he's actually putting 40.20 in for B, how much does he actually pay? Well, he pays 40.20 and he pays that 36 times. So when we multiply that, we can see that he actually paid $1447.20. But here's the thing. He paid $1447.20. The laptop only cost $1,200. So he actually paid, when we subtract those, $247.20 in interest. So we say, therefore, he paid $1447.20, of which $247.20 was interest.